skill.
We're going to make a start now. So thanks so much for coming and welcome to our Oxford Energy Network seminar. My name is Tina Fawcett. I'm the network convener. Before introducing today's speaker, I'm just going to go through a couple of other things that are happening in the Oxford Energy Network and with the Zero Institute. So hopefully most of you are signed up to the Energy Lunch, which is happening this Friday, 12 till 2 p.m. in the School of Geography. So if you have signed up, please come. It'd be lovely to see you there. The second thing is to mention the Oxford Energy Network newsletter. If you're not signed up, please have a look at our website, which is energy.ox.ac.uk, and you can sign up there, and that means you'll find out about all the weekly seminars, but also other news that's happening within Oxford and outside of it about energy. And you can, if you want to do social media, we're on Blue Sky now, so please see us there, and again, interact with us. That would be nice. Next week, which is the last week before we break for the end of the teaching term, we've got Chris Jardine, and his talk is called The Astonishing Rise of Solar PV. Some of you will know Chris. He's been a sort of solar energy academic and then an entrepreneur and business person for decades now, and he's sort of reflecting back on what he's seen over his time in the business and in academia, and he's a very good speaker, so that should be a really nice event. And we're going to follow it with sort of drinks and snacks at the end to sort of celebrate we've got to the end of term parade. So please come to that. That would be nice to see you. The final thing to say before introducing our speaker is that we know some of you may have to leave at 6 o'clock. The seminar goes on till 6:15, so if you need to leave, please do, that's fine. So today's speaker is Yanis Papakonstantinou. Hey. And his topic, as you can see, is harvesting energy from the cold universe, the missing piece in the renewables puzzle, question mark. And question marks in titles, as we know, are always a bit tricky, because if it's in a headline, the answer is always no. That's Bettridge's law newspaper headlines. But hopefully if the answer was no, you wouldn't have made it your question. So, so Yanis is a professor of photonics and nanofabrication at UCL, and he leads the photonics innovation lab there. And before joining UCL, he worked at CERN, and he also worked at Sharp Laboratories. His research focuses on light and matter interactions at the micro and at the nanoscale, and it's got multiple applications, his research work. And of the list he sent us, just two are radiative cooling and biomedical devices. And he holds a diverse portfolio of patents in 15 different areas. So as you can see, his research has sort of got a wide range of implications, and we look forward to finding out the answer to the question today.
Thank you very much, Tina. Thank you. And indeed, one of the main objectives of this talk is to remove the question mark here. All right. Okay. Before I start my talk, should say that this is a topic that really speaks to my heart. I come from Greece. It's a very hot country, increasingly suffering from heat waves. As a matter of fact, just last year in the summer, we had more than 3 weeks of over 35 degrees. My dad suffers from a heart condition. It meant that he couldn't leave home for more than 3 weeks other than very early in the morning. And it gets to show that heat stress actually affects the most vulnerable parts of the population, people with chronic illnesses, infants, and so on. As well as where I come from is outside Athens, where in 2018, wildfires erupted due to the very dry conditions and another extreme heat wave, which resulted in over 100 people dying. So really, I have personal issues with global warming, so I decided to do something about it. And I hope I can persuade you that this is the right direction. So the objectives of my talk, first of all, I would like to make the case that cooling is really an obstacle in our path towards net zero transition. The second objective is I would like to establish radiative cooling as a viable and electricity-free alternative to traditional cooling methods, such as, for example, vapor compression, air conditioning units, and so on. Hopefully, I will persuade you that the cold universe can become an additional renewable resource in the fight against climate change. So we can do way more than just cooling surfaces down via this process that's called radiative cooling. And the final objective of the talk is to raise awareness in the field, because there are very few groups in the UK and in Europe, actually, that are active in this area. And if we want to make strides in this field, we need to combine a lot of skills, and we need more people coming into this area and helping us achieving our goals. Right, let's start with the first objective, to persuade you that cooling is a real problem. As you can see, out of the 10 hottest global years on record, most of them, well, the 10 hottest global years on record all occurred after 2014. And this is quite alarming even for continents like Europe, which have a relatively cool climate. As a matter of fact, there was a study by the Copernicus Climate Institute that was made the headlines a couple of years ago, which saw that Europe is warming twice as fast as other continents. So this is a problem that doesn't affect only, the relatively and traditionally warmer parts of the region, like, for example, near the equator, but increasingly it becomes a problem for regions like ours. Now, there was a very nice study that corroborated these findings from friends and colleagues from Oxford University. Jesus is here today with us. So basically what they found through the study is that they examined what will happen as the global temperature rises from 1.5 to 2 degrees, and they examined the relatively change in cooling degree days. And for those not familiar with cooling degrees days, this is an indication of when cooling is needed in our houses. So what they found is that out of the 10 countries that will be mostly affected, 8 are in Europe, and right at the top is the United Kingdom. There's now a wealth of data supporting this. For example, a study from the Met Office showed that by 2050, the probability of extreme heat waves in the UK will increase by 35 times. There was more studies by the Climate Change Committee that was commissioned by the UK Parliament, indicating that even during mild summers, over 20% of UK houses overheat. Now, what happens as, of course, the Earth is warming up, that drives consumption for air conditioning. 2024, the electricity consumption due to space cooling exceeded 2.4 thousand terawatt hours. And of course, with that comes an enormous amount of CO2 emissions, which exceeded about 1.3 gigaton. Now, the problem is not that these numbers are large as they are already, is that the demand for cooling is growing, and is growing in double digits. Okay, so there is this notion, particularly in the developing world, in low and middle income countries, when people increase their income, the two first consumer products they buy is a car and an air conditioning. Yeah. Now, according to the International Energy Agency, by 2050, over 300 million AC units will be sold per year. By the way, I had the honor to be invited by the Department of Energy Security and Net Zero to join the UK delegation at the International Energy Agency. I was participating in Annex 92, which is smart materials for sustainable heating and cooling buildings. So now we have to deal with what is known as the Great Cooling Paradox, whereby we need to achieve net zero at the backdrop of explosive demand for new cooling capacity. So how are we going to go about to do it? And this is the last doomsday slide to make things even worse. Well, the urban heat island is a very important effect. We know very well that the temperatures in the centers of cities is considerably warmer than the suburban areas, sometimes exceeding 5 degrees. And the big contributor in this case is the AC units. So there are several studies in the field. About 1.5 to 2 degrees is due to the AC units. Okay, so we really have to find an alternative way of cooling down our houses. Right. So I'm going to gradually start shifting towards the second objective of my talk, which is to establish radiative cooling as a green solution to the problem that I have just presented. What's radiative cooling, first of all? Well, this is the natural thermoregulation process that sustains the temperature on Earth within the living zone. A particular example is the rapid cooling down of deserts at night time. So how is this happening? There's no any weird phenomenon happening with the microclimate in deserts. This is simply due to the fact that during daytime, the sun is absorbing a lot of the solar radiation, it's heating up. But when the sun goes away, the sand, which is mostly made of silica, and silica is a highly emissive material, evacuates its heat, which goes through the atmosphere and escapes to the universe. And this is particularly effective in deserts because they have dry climate, so there's no water, which is a non-greenhouse gas. Sometimes the temperature difference in the Sahara can exceed 45 degrees just to solve the efficiency of the cooling process, the radiative cooling process. Now, let's dig into the details. What I'm showing here is all the thermodynamic resources participating in radiative cooling. First of all, we have the sun, and of course, the sun is warming up our planet. At the same time, the Earth is emitting mid-infrared radiation towards the universe, and there is an intermediator between the Earth and the universe, of course, the surrounding atmosphere. Now, the reason why there's this coupling between the Earth and the universe, which, by the way, has an infinite heat capacity, and if you think about that, the Earth is just a tiny hotspot in an ocean of, ultra-cold universe, which is very close to the absolute zero temperature. The reason why this coupling is allowed is because the atmosphere is semi-transparent to the mid-infrared emission coming from the Earth. Now, of course, when we're talking about the emissions, we should quantify how much of this in terms of power. And it's an enormous amount of energy that's emitted by Earth at the order of 10 to the power of 17. It's very close to the energy that we're receiving from the sun minus radiative forcing, which is causing the global warming. 10 to the power of 17, it is orders of magnitude more than the primary energy generation. So if we could only harvest a tiny fraction, less than 0.1%, then that would be sufficient in order to power up all our ambitions. So this is basically what I'm trying to do in my group, as well as multiple other groups around the world. Now, if we want to represent all of these processes into their equivalent spectra, so what I'm showing here on the horizontal axis is wavelength, and the vertical axis is irradiance. First of all, we have the solar radiation. The solar radiation extends from the UV all the way to near infrared. And if we take the prototypical AM 1.5 spectrum, the integrating intensity is about 1,000 watts per meter square. At the same time, we have the black body radiation. Basically, it is all the heat that's emitted by any object on the surface of Earth. And that extends from about 3 microns to 50 microns. Okay? And with the blue area here, I'm showing the emissivity of the atmosphere. And by Kirchhoff's second law, when I'm talking about emissivity, this is the same as the absorption. So where the emissivity is 1, the atmosphere is opaque to these wavelengths, whereas when the emissivity drops to 0, then the atmosphere becomes transparent. And as it so happens, where the black body emission peaks, the atmosphere is very transparent. And this is the principle behind radiative cooling, because that opens up a channel in order to couple the radiation that comes from the surface of objects on the Earth to the universe. Now, it is a lucky coincidence as well that there is no overlap between solar radiation and black body radiation, which for people like myself, we're photonic engineers, we're photonic scientists, this is real heaven, because we can engineer surfaces in a way that they behave in some way with solar radiation, but they do something completely different to black body radiation. We can have sort of orthogonal response to the photonic properties of the surface. It's something that we'll elaborate a bit in the following slide. Right, so if we zoom in on the surfaces right on Earth, and what I'm trying to show here is all the heat flux, all the heat exchanges between the surfaces and their environment. Now, there are 3 incoming heat fluxes. The one that comes from the sun, so any radiation that is absorbed by any surface, what results in heating it up. You also have the atmospheric emissions. The atmosphere itself emits heat towards the surface, or it could be from any other object or structure around you. Imagine that you have a tall building that's at some temperature, it's emitting heat towards the surface. These are all included here. And the last incoming heat flux is what we call the parasitic heat flux due to convection and conduction. Now, the sole outgoing heat flux is due to the surface's own radiation. And what we are trying to do as radiative cooling scientists is to engineer the properties, the material properties and the structural properties of the surfaces in a way that this outgoing heat flux surpasses the sum of the three incoming fluxes. And in this way, we can achieve an equilibrium temperature which is below the ambient. And hence, we can passively cool down the surface. Now, if we go back to the spectra graph that I showed before, what I'm going to do here is I'm going to put some values on the properties that the surface itself should have in order to achieve radiative cooling. First of all, it should have a reflectance, which is 1, particularly across the solar wavelengths. If the surface reflects all the solar radiation, then it becomes an irrelevant actor. It doesn't matter it is out there. And so we can extend this radiative cooling phenomenon not only during nighttime, as it happens in deserts, but during the full 24-hour cycle. At the same time, the emissivity of the surface, and the emissivity and the reflectance of the surface, they're not independent quantities. They are related by this very simple relationship. Should be 0, so the surface should not absorb anything, but suddenly it should emit very, very strongly between 8 and 13 microns. And in this way, we minimize the solar heat flux, minimize everything that comes from the surrounding atmosphere, and maximizing this Q-cool component. And so to satisfy this equation. But what I have left is this parasitic heat component. And actually, this is the Achilles heel in the field. This is something that has been overlooked, but it's really essential, as I will present now. Now, one question that comes up all the time is, what are the thermodynamic limits for cooling via radiative cooling? So how far can we go with this process? So what I'm presenting in this graph is the temperature reduction below ambient as a function of the net cooling power. The net cooling power is Q-cool minus all the incoming heat fluxes. Now, what happens at the beginning of the process? A surface emits maximum heat, but as its temperature goes down, of course, the heat it radiates reduces up to the point that you have an equilibrium situation. The surface reaches a steady state when the outgoing heat flux balances out the incoming fluxes. This is where the surface attains its final temperature. So for the vast majority of the systems that have been presented so far, the parasitic heat losses are very high. They're usually represented by what we call thermal transmittance, the same as in any insulation system. And the thermal transmittance is typically on the order of 10 watts per meter square Kelvin, which means that the equilibrium is at under 10 degrees. So most of the system in the literature can go up to 8 degrees below ambient. Now, there's a very nice thermal circuit representation. So in the radiation is emitted, the heat that's emitted by the surface is represented by a current source. And of course, the objective is to deliver as much power as possible to a cooling load, basically the object that you're trying to cool down. But what happens with the parasitic heat losses, they appear as a shunt resistor. So rather than going through your load, it goes through the parasitic resistor. So you're not able to deliver as much cooling power as you would otherwise do. But what happens if this is reduced, say, by an order of magnitude down to, say, 1 watt per meter square Kelvin? This is, by the way, absolutely possible with today's technologies. The double glazed window has that type of thermal insulation. So now suddenly you have a dramatic change in the cooling power, and the system is able to equilibrate at 45 to 50 degrees below ambient. We're talking about completely passive refrigeration, deep refrigeration. Okay? Now, of all these parasitic heat-free systems, of course, the main challenge is to reduce the parasitic heat losses while maintaining compatibility with radiative cooling. And this is a formidable challenge. It has only been demonstrated once with a very complicated system, but I was very fortunate. In 2024, I was awarded an ERC Advanced Grant, the objective of which is really to bridge this gap between what the literature is today to what the thermodynamic limits dictate. By the way, the analogy that I give is in radiative cooling, we are today where silicon solar cell research was about 30 or 40 years ago, where it took several decades in order to reach the future limits. Only that we don't have 5 decades. We have to go there, and we have to go there very, very quickly. Now, a little bit of history. Radiative cooling is an area of research that has been known for many decades. This is the pioneering work by Claes Granqvist from Sweden, and someone who had the pleasure to meet over several occasions and receive his advice. So this is a system that he put on the roof of Uppsala University. At the time it was Stockholm University, and it was a very simple system. Basically, they had a silicon oxide coated aluminum plate. This was only a nighttime system. It wasn't operating during daytime, but they did so. They did a lot of the foundational work. They did so that its passive cooling is absolutely possible. So when I asked Claes, why did you drop this line of research, he said it was impossible to find any funding at that time. Now, the field went through a quiescent period for about 3.5 decades until 2014, 2015, where Aswath Raman, at the time he was a PhD student at Stanford with his advisor, Sarpui Fan, now he's a professor at UCLA. They came up with this ingenious design. Basically, they built a multi-layer distributed Bragg reflector. And in doing so, they arranged the thickness and the materials in a way that they achieved almost complete solar reflectance. And as you can see here, a selective emissivity. And by the way the system works is every time light finds an interface between 2 different materials, it is reflected. And if you arrange the phase of this elementary wave so that they're all in phase in the backward direction, so you build up a highly reflective field. They put the system on the roof of the university, and they demonstrated the first daytime radiative cooling system, and they measured a temperature drop of about 4 to 5 degrees. Now, up until then, you could hardly find 10 papers in the field being published. Last year, I think there were more than 2,000. So this paper really set the whole field alight. Since then, the researchers have focused their efforts in creating more scalable systems that are cheaper, systems that can be applied, over large areas, and polymer films that can achieve radiative cooling. We have coatings and paints. We even have colored, aesthetically pleasant kind of systems that have some color can be applied, on the roofs of houses. Now, I'm going to slightly change here. I'm going to talk a little bit about the applications of radiative cooling. And of course, the first target, evidently should be buildings due to how much they weigh in the energy consumption. About 40% of the primary energy consumption happens in our buildings, most of it for heating and cooling them down. As a matter of fact, in the United States, sometimes over 60% of the electricity consumption of some houses goes towards the air conditioning units. The problem that we have, and that dictates some really serious building engineering, is the fact that just by cooling down the surface doesn't mean that you will cool the interior of the building. Imagine that you have a roof that is very well insulated, so you're not going to pass on these gains. So there are lots of engineering challenges and lots of very nice designs in order to, pass on this cooling into different floors of the building. So it's a very active area of research. That's outside my own expertise, but I know that Jesus is working in this area. I'm happy to collaborate if you have any ideas. Now, the second main application is passively cooling of vehicles, particularly electric vehicles. The reason for that is we spoke to several car manufacturers as well as TfL, and I'm going to show later on a slide with TfL. And they've told us that actually this is a significant problem because in the summer, on a hot day, sometimes about 30 to 40% of the battery consumption goes to the air conditioning. And so that means that it significantly reduces the range of the vehicle. In the case of TfL, they told us that they need to recharge the buses quite frequently. And there are two lines of research here. One is to create these radiative cooling covers for when the car is parked, because most of the heating of the cars happens when they are parked. So when we were younger, we were going to the beach place, we leave the car, we would go back and it was as hot as an oven. So the first thing we do is put the windows down and blast the car with an air conditioner for 15 minutes before we're able to use it. And the second, if you want, line of research is trying to integrate radiative cooling directly to the rooftop of the cars, or as well as the body of the car. Now, a very interesting application is personal thermal management. So people have come up with a lot of systems, a lot of designs where they're knitting these radiative cooling materials into fibers, and then they're making clothing. Of course, the challenge there is that they have to interact with the human body, and they have to allow a process like, for example, transpiration. So really, in addition to radiative cooling, a new challenge is how to change the wetting properties, if you want, of these fibers in order to allow this natural ventilation process of the human body to take place. Now, a last application that I want to discuss, this is one of my favorite, is in horticulture. Why is cooling horticulture important? It's important because heat stress really affects plant growth. It inhibits photosynthesis. It slows down photosynthesis. Now, at the same time, when under very hot conditions, you have very rapid evaporation of water. It means that you need to water the plants more frequently. So there's a lot of water consumption taking place. Now, again, there's two general directions. One is to cover, if you want, the greenhouse with radiative cooling films and keep a greenhouse warm, cold. Or the best option, in my opinion, is to create what is known as radiative cooling mulching film. And mulching films is, they're very well known. If you've ever been in the field, you probably have seen some of them. So basically, they're plastic films that cover the soil and keep the soil in place, as well as it keeps the humidity in the soil. It stops evaporation. So there was a very nice study that happens in 2024, where they created these radiative cooling films, and it was real test in the field, and they grown this leafy Chinese cabbage, and they found that it increased the mass of this plant by 124% compared to when it was grown in areas that didn't have mulching film. Right. So what I did promise, however, is to establish radiative cooling as a new renewable resource, and I think we have to do way better than just cooling the surface down. And in order to do that, I need to take a step back and introduce a heat engine, because if you are to use the cold universe as a renewable resource, you should at least be able to generate electricity. I think this is really the test that a renewable resource does, or improve the efficiency of the process. Okay? Now, what I'm showing here is a typical Carnot engine. Basically, a Carnot engine works by taking advantage of the temperature difference between a hot reservoir and a cold reservoir by installing a heat engine between these temperature differential. One can extract useful work. In the case of a Carnot engine, we're talking about the efficiency of the process. The efficiency of the process, in an ideal case, depends only on the temperature of the hot and the cold reservoir, and it's given by this equation here, where on the numerator you have the temperature differential, and the denominator will have the temperature of the hot reservoir. So what I'm plotting here is the Carnot efficiency as a function of delta T, the delta T is here, for a constant temperature of the hot reservoir. Okay, so basically what happens as you start reducing the temperature on the cold reservoir. And what you see here, this is for 3 different temperatures corresponding to low grade, medium grade, and high sources. What you see here is a linear increase to the Carnot efficiency. So basically, if you expose the cold reservoir to the cold universe, you can immediately improve the efficiency, say, for example, of a steam engine. Something even more interesting happens in the case of the refrigeration cycle. And by the way, there's a duality between the Carnot, the heat engine and the refrigeration engine, in that the refrigeration engine is the reverse Carnot cycle. And what happens here in a typical refrigeration engine, our fridges, our AC units, what you're trying to do is you're trying to extract heat from the cold reservoir and dump it into the hot reservoir. And in this case, you need some input work. And usually, we don't use the term of efficiency, but we use the coefficient of performance. And the coefficient of performance is the ratio between the heat that is rejected to the hot reservoir over the work required in order to achieve it. And in this case, the differential temperature appears on the denominator, which now means that by reducing this TC, you can have a non-linear improvement of the coefficient. So if you were able to couple this radiative cooling refrigeration, you can actually achieve very significant gains, even achieve energy-free refrigeration. Now, this is how we do it in radiative cooling. If we want to improve the heat engine, then we expose the cold side of the universe. This is the one that is losing heat. Whereas if we want to improve the efficiency of the refrigeration engine, then it is the opposite. It is the hot side that needs to be exposed to the universe. Just to give you a couple of quick examples of this. A prototypical example in the field is thermoelectric generation. Thermoelectric generation leverages the Seebeck effect. Basically, it translates temperature gradients into voltage, and so useful electricity. In traditional thermoelectric materials, it is usually the hot side that's exposed to the heat source, and the system works by heating up the hot side, whereas the cold side is usually at ambient temperature or slightly above the ambient temperature, 5 to 10 degrees above the ambient temperature. In a thermoelectric material operating under radiative cooling, it's the opposite. It is now the hot side of the thermoelectric material that's exposed to the universe, and by reducing its temperature, you can actually generate electricity even at night. Now, there have been some really nice studies where they try to co-harvest, if you want, the 2 main thermodynamic resources, the sun and the universe, by exposing the hot side to the sun and the cold side to the universe. And this is very important because a lot of the times we're talking about competition. All of them, they occupy areas. So, by synergistically taking advantage of these 2 resources, there's no competition anymore, and you can improve the efficiencies even more. Another application of very special importance is how to improve the efficiency of solar cells. And of course, we know that when a solar cell is being heated up, and in the summer, sometimes solar cells operate at a temperature in excess of 50, even 60 degrees. For every degree above 25 degrees, the efficiency of a solar cell of a crystalline silicon solar cell reduces by between 3 to 0.5%. So you can imagine that if you go up to 60 degrees, then you have a 15% loss in solar cell efficiency. So people have come up with a lot of designs in order to integrate radiative cooling with solar cells to reduce their temperature. Of course, the challenge here is that you should allow the majority of the solar radiation through in order for the solar cell to operate. Now, if we move to the refrigeration engines, here we have a complexity in that somehow we need to integrate radiative cooling, for example, with an AC unit. So these are two strategies that are typically employed. And now I'm going to give a second analogy with solar cells. In the field, a very popular solution is creating radiative cooling panels, and in the same way as we have a solar panel, and rather than have electricity running through, we have water running through. So we have hot water on one end of the radiative cooling panel, cold water coming on the other end, and then coupling it via heat exchanger, for example, to an air condenser of a split AC unit. By the way, again, as a rule of thumb, for every degree of temperature drop on the air condenser, the efficiency of an AC unit improves by 3%. That's an enormous amount. A second strategy, if you want, is to industrial systems where they usually operate with a cooling tower, and there you have an enormous amount of water loss. For electricity purposes, last year we consumed more than 50 trillion gallons of water, mostly towards cooling, or for example, in concentrated solar power plants. So the idea here is to integrate this radiative cooling with the cooling tower. Some of the heat rejections happening on the cooling, on the radiative cooling panels, leaving a bit less to the cooling tower, and so you have significant savings of water. This is how a setup of radiative cooling panels looks like. This is property of Engie Krigenlab, the French utility company that we collaborate with. You can see underneath the pipes for the water running. So the radiative cooling is on top of them, and there's water running through them in series in order to cool it down. Right. I want to give you an example of the kind of efficiency one should expect if you integrate radiative cooling with a split AC unit. We're talking about this configuration where you install the radiative cooling panels of the roof of the building, and then essentially what you're trying to do is you're trying to cool down the condenser of the AC unit. So what I'm showing in this graph, I have taken like a standard example of a standard example of a split AC unit. It works with an isentropic efficiency of 8%. It has a refrigerant of R134 and so on. And basically, I couple the radiative cooling panel. And what I'm showing here on the horizontal axis is the differential temperature, and on the horizontal axis, the electricity savings as well as the coefficient of performance. And underneath in the second graph is the panel to floor area ratio, because of course, you need to occupy some area with the unit. And this is quite important to understand how much you need. Now, typical AC units have a condenser that operates to between 5 and 10 degrees above the ambient temperature. So the coefficient of performance is at best 4 or 5. Standard radiative cooling that you find in the literature can reduce the temperature by up to 5 degrees, and you can have an electricity saving at maximum 40%. But if you use a parasitic-free radiative cooling without the parasitic heat losses, then you can really push the system towards coefficient performance of 100% or almost 80 to 90% electricity savings. So this kind of system can really bring a breakthrough. Now, what is also very important is that by cooling down the condenser, that's an image of an AC unit. What you're doing is essentially you are removing directly heat from here. So essentially, you're also mitigating at the same time the urban heat island effect. And it's quite way more efficient than having a solar panel powering up your AC unit, because there was a study published in 2024 that has shown that having solar panels on a roof of buildings in cities can actually positively contribute to urban heat island, because themselves become very hot. So if you have radiative cooling panels, then not only do you mitigate the heat here, but you mitigate the heat from solar panels. All right. How long do we still have? Okay. So I'm going to very briefly talk about the work that we do in my group in the radiative cooling field. We cover all these areas. We make radiative cooling coatings, films. We have created our own radiative cooling glass. We make self-adaptive systems that understand the ambient condition and change the properties. We're working towards passive refrigeration. We really like, we have a new grant on horticulture. We're looking into improving the efficient heater refrigeration. And finally, we have created radiative cooling maps. Of course, there's not enough time to cover all of these. I'm just going to start with a radiative cooling coating that we have developed in my group. And if you have a coating, it should satisfy a very long and demanding list of requirements. For example, it should have a low environmental impact. Mostly, it should be PFAS-free. It should not contain any fluorinated substances. It should have very low volatile organic compounds. It should be mechanically durable. It should be UV resistant. It should resist pollution, dust, and chemicals. It should resist moisture. It should adhere well on most substrates. So it's a very demanding list of requirements that it has to fulfill. So the first generation of coatings that we have developed uses polyethylene combined with polydimethyl siloxane. And the reason why we use these two organic components is because polyethylene is a very inert material. These are, by the way, the FTIR peaks. These are the absorption peaks of the organic compounds that we use in our system. It has zero absorption in the solar spectrum and in the MIR window, whereas PDMS, it concentrates all its heat emission within the MIR window. So if you combine the two as a system, you have nearly ideal conditions for radiative cooling. Of course, you cannot just mix two components and suddenly expect that you will cool down a system. You have to be a little bit more innovative. What we did in our case, we came up with a very simple and scalable deep coating process, whereby we took polyethylene, we dissolved it in the solvent, and then we created with an organic emulsion process PDMS particles. We mixed everything together. We deep coated a substrate, and then we did a solvent exchange and a phase separation. And what came out of this is this porous material. And the porous matrix is made of polyethylene, whereas inside we have the PDMS particles. And this is an EDAX, basically confirming that the silicon contact of the PDMS particles, whereas it's surrounded by a carbon contact with the polyethylene. Now, why do we want to use porous material? Because as I said, you need to have very high solar reflectance. And how do we achieve solar reflectance? This is a light diffusion process. Light undergoes multiple scattering events until eventually it is back reflected. This is the reason why we went through this tedious process, if you want, in order to create the porosity. Basically, the pores and the pore size is also very important because it determines how efficient is the scattering process. This is the pore size distribution as we characterize with mercury porosimetry. And this is the optical mean-free path as a function of wavelength. So essentially, the goal of any photonics engineer is to minimize the optical mean-free path. Optical mean-free path is the distance between subsequent scattering events. And if you have a very small distance, it means that you create a highly scattering and a highly reflecting material with a minimum thickness. So you have gains in terms of cost, in terms of weight of the material, and so on. Now, we experimentally measured our system, and we found that the solar reflectance is about 97, 98%, which is basically better than the best metal reflectors. We have an emissivity that exceeds 0.9. And we also took this in the field. This is the roof of Mallet Place Engineering building at UCL, where we have our own weather station. And we tested this under real conditions, in outdoor condition. This is, by the way, the fingerprint of our sample under an MIR camera. And this is a commercial white paint where you can see evidently that our sample is at substantially lower temperature. And we actually measured the temperature with a thermocouple on our sample against the ambient temperature, the blue line, whereas the sample, the temperature on our sample is the red line. And this is the first demonstration of radiative cooling on UK soil. but for 36 continuous hours, we got cooling of about 4 to 5 degrees. There's a very nice correlation between the amount of cooling and the solar radiation, which basically indicates cloud coverage. And the main, if you want, enemy to radiative cooling is moisture, is water, and is cloud cover. It's a renewable resource in the same way that, if the wind doesn't blow, you do not generate electricity. But in the lines, then when the clouds are out, you don't get much radiative cooling. Now, we are now in the generation 20 of our coatings, and the main objective is for them to be durable. And also to be able to apply it with other techniques, like, for example, spraying or brushing as any other traditional coatings. And we have come up with two different formulations. One is water-based, and this is compatible with buildings and low volatile organic components. And one is solvent-based, that is more appropriate for vehicles. What I'm going to show here is tests that we have performed. Basically, it's a standard test that measures the abrasion resistance of coatings. Most commercial coatings that are for outdoor application can survive up to 4,000 cycles. In our case, we survive 20,000 cycles. In addition to, because we were based our coating on marine type of coatings, we managed to achieve very good water repellency. So we created a super hydrophobic coating that can clean itself, so that can resist pollution from, for example, pollution or contaminants. All right. In October 2024, we installed our coatings on a few mock buildings. This is through our participation in the process here. These buildings were constructed by Acciona. And the objective of this is, these are fully sensorized buildings. They have an AC unit inside that maintains the temperature within the buildings constant. And the objective here is to measure how much the energy consumption is compared to another pilot building that has a commercial building. And as I mentioned, TfL approached us, and we very generously they made available 5 electric buses, which we will coat with our radiative cooling paints this summer. And the buses will follow different routes. One will go through the center of the town of tall buildings and so on. Another one will take a more suburban route. And then there we will see how often they need to be recharged. So I think I need to put a full stop here.